NENOMATICA, where mathematics meets YouTube excellence. Let's start with our example. We are asked to solve the equation where 27 to the power of x equals 2, and then find the value of the expression 3 to the power of 6x plus 9 to the power of 3x plus 27 to the power of 2x. First, we need to solve for x from the given equation, 27 to the x power equals 2. Let's rewrite 27 as 3 cubed to better work with its exponent. Now we can apply the power to power rule, which states that when a power is raised to another power, we multiply the exponents. So 3 cubed to the power of x becomes 3 to the power of 3x. To solve for x, we'll take the natural logarithm of both sides. This will bring the exponent down as a coefficient. Now we solve for x by dividing both sides by 3 times the natural log of 3. Now that we know x equals ln 2 divided by 3 ln 3, we can substitute this value into the expression 3 to the power of 6x plus 9 to the power of 3x plus 27 to the power of 2x. Let's rewrite each term using base 3. 9 equals 3 squared, and 27 equals 3 cubed. Now we apply the power to power rule, again to simplify. 3 squared to the power of 3x becomes 3 to the power of 6x, and 3 cubed to the power of 2x becomes 3 to the power of 6x as well. We can now combine these like terms since they all have the same base and exponent. We have 3 identical terms of 3 to the 6x, which gives us 3 times 3 to the 6x. Now, instead of directly substituting our complex expression for x, let's take a different approach. Since we know 27 to the x equals 2, we can use this fact to simplify our expression further. We can use the property of exponents that states a to the m plus n equals a to the m times a to the n. Since we have 3 to the 6x, and we know that 3 to the 3x equals 2, we can rewrite 3 to the 6x as 3 to the 3x squared, which is 2 squared. Now we can compute the final answer. 3 times 2 squared equals 3 times 4, which equals 12. Let's start with the following example. If a raised to the power of 5 equals 10, we need to find the value of, first, a raised to the power of 20. Second, a raised to the power of negative 15. Third, 2 times a raised to the power of 5. And fourth, the quantity 2, a raised to the power of 5. Let's solve the first part, a to the power of 20. We know that when we have a power raised to another power, we multiply the exponents. So we can rewrite a to the power of 20 as a to the power of 5 raised to the power of 4, which equals 10 to the power of 4. And 10 to the power of 4 equals 10,000. Now, let's solve the second part, a to the power of negative 15. We can express this in terms of a to the power of 5 as well. A negative exponent means 1 over the positive exponent. We write a to the power of negative 15 as a to the power of 5 raised to the power of negative 3. This equals 10 to the power of negative 3. And 10 to the power of negative 3 equals 1 over 10 cubed, which is 1 over 1,000, or 0.001. For the third part, we need to find the value of 2 times a to the power of 5. Since we already know that a to the power of 5 equals 10, we can simply substitute this value. 2 times a to the power of 5 equals 2 times 10, which equals 20. Finally, let's solve the fourth part, 2a in parentheses raised to the power of 5. When we have a product raised to a power, we raise each factor to that power and then multiply. So 2a in parentheses raised to the power of 5 equals 2 to the power of 5 times a to the power of 5. 2 to the power of 5 equals 32, and we know a to the power of 5 equals 10. Therefore, 2a in parentheses raised to the power of 5 equals 32 times 10, which equals 320. Let's summarize our solutions. A to the power of 20 equals 10,000. A to the power of negative 15 equals 0.001. 2 times a to the power of 5 equals 20. And 2a in parentheses raised to the power of 5 equals 320. Let's look at the problem. Let's start by working with the first part of the equation, where we know that 4 to the power of x equals 100. We need to find the value of x first, which will help us determine the value of 2 raised to the power of 3x minus 1. Now we can rewrite 4 as 2 squared, which gives us 2 squared to the power of x. Using the power rule, this is equivalent to 2 raised to the power of 2x. Next, we need to express 100 in terms of base 2 as well. We can write 100 as 10 times 10, and since 10 equals 2 to the power of x times 2 to the power of x, which means that 100 equals 2 to the power of x times 2 to the power of x times 2 to the power of x times 2 to the power of x. Since we have 2 to the power of 2x equals 100, and 100 equals 10 times 10, we can determine that 2 to the power of x must equal 10. Now that we know 2 to the power of x equals 10, let's use this to find the value of 2 to the power of 3x minus 1, which is what the problem is asking for. We can rewrite 2 to the power of 3x as 2 to the power of x raised to the power of 3. Since we know that 2 to the power of x equals 10, we can substitute this value. All that's left now is to calculate the value. 10 cubed equals 1,000, and 1,000 divided by 2 equals 500. Therefore, the value of 2 to the power of 3x minus 1 equals 500. To summarize, we first found that 2 to the power of x equals 10 by rewriting 4 to the power of x as 2 to the power of 2x, and then using that information to calculate that 2 to the power of 3x minus 1 equals 500. Let's look at our problem. If 2 raised to the power of x equals 10, then we need to find the value of 1/8 raised to the power of x plus 2. Let's begin solving this problem. First, we'll rewrite 1/8 in terms of powers of 2. 1/8 equals 1 over 8, and 8 equals 2 cubed, so 1/8 equals 1 over 2 cubed, which can be written as 2 to the negative 3 power. Next, we'll use the power rule for exponents, which states that when we have a power raised to another power, we multiply the exponents. So 2 to the negative 3 power, all raised to the power of x plus 2, equals 2 to the power of negative 3 times quantity x plus 2. Now, we'll distribute the negative 3 to the terms inside the parentheses. Negative 3 times x plus 2 equals negative 3x minus 6. Using the product rule for exponents, we can split this into a product of 2 terms, 2 to the power of negative 3x times 2 to the power of negative 6. Let's calculate 2 to the power of negative 6. This equals 1 over 2 to the 6th power, which is 1 over 64. Now, we need to use the information given in the problem. We know that 2 raised to the power of x equals 10. Therefore, 2 raised to the power of negative 3x equals 2 to the power of negative 3 times x, which we can rewrite as the power of negative 3 of 2 to the power of x. This means we have quantity 2 to the power of x, all raised to the power of negative 3. We can now substitute the given value. Since 2 to the power of x equals 10, we get 10 to the power of negative 3 times 1 over 64. 10 to the power of negative 3 equals 1 over 10 cubed, which is 1 over 1,000. Finally, we multiply the fractions. 1 over 1,000 times 1 over 64 equals 1 over the product of 1,000 and 64, which is 1 over 64,000. Therefore, if 2 to the power of x equals 10, then 1/8 to the power of x plus 2 equals 1 over 64,000. First, let's solve the problem. If 2 raised to the power of x equals 10, then find 32 raised to the power of x minus 1. Let's start by writing out our target expression, 32 raised to the power of x minus 1. Using the properties of exponents, we can rewrite this expression as 32 raised to the power of x times 32 raised to the power of negative 1. Now, 32 to the power of negative 1 is equal to 1 over 32. We know that 32 equals 2 raised to the power of 5. So we can rewrite 32 raised to the power of x as 2 raised to the power of 5x. Using the power of a power rule, we can simplify 2 raised to the power of 5x as 2 raised to the power of x raised to the power of 5. Now we can substitute the given value. Since 2 raised to the power of x equals 10, we can replace 2 raised to the power of x with 10. 10 to the power of 5 is 100,000. So our expression becomes 100,000 divided by 32. If we calculate this division, we get 3,125. Let's try another example. If 5 raised to the power equals 7, and 7 raised to the power b equals 5, then find 5 raised to the power 2ab. Let's begin by writing our target expression, which is 5 raised to the power 2ab. Using the power of a power rule, we can rewrite this as 5 to the power raised to the power 2b. From the given conditions, we know that 5 to the power equals 7, so we can substitute that value. We can rewrite this as 7 to the power b squared. Now, we know from the given conditions that 7 to the power b equals 5, so we can substitute that value. 5 squared is 25. If 5 to the a equals 7 and 7 to the b equals 5, we want to find the value of 35 to the ab power. Let's solve this step by step. First, we'll rewrite 35 to the ab power. We can express 35 as 7 times 5. So we have 35 to the ab equals the product of 7 and 5, all raised to the ab power. Next, we can apply the product to power property, which states that when a product is raised to a power, it equals the product of each factor raised to that power. So we get 7 to the ab power times 5 to the ab power. Now, we'll use the power to power property. When an exponential expression is raised to another power, we multiply the exponents. So 7 to the ab becomes open parenthesis 7 to the b close parenthesis all to the a power. Similarly, 5 to the ab becomes open parenthesis 5 to the a close parenthesis all to the b power. From the given conditions, we know that 7 to the b equals 5 and 5 to the a equals 7. So let's substitute these values. 7 to the b to the a power becomes 5 to the a power, and 5 to the a to the b power becomes 7 to the b power. From our given conditions, we can now substitute 5 to the a equals 7 and 7 to the b equals 5. This gives us 7 times 5. Finally, we multiply 7 and 5 to get 35. Let's try another example. If 5 to the a equals 7 and 7 to the b equals 5, we want to find the value of 125 to the a plus 1 power. For this problem, we need to recognize that 125 equals 5 cubed. So let's rewrite 125 to the a plus 1 power as open parenthesis 5 cubed close parenthesis to the a plus 1 power. Now we'll use the power to power property again. When an exponential expression is raised to another power, we multiply the exponents. So we get 5 to the 3 times a plus 1 power. Next, let's distribute the 3. 3 times a plus 1 equals 3 a plus 3. So we have 5 to the 3 a plus 3 power. We can rewrite this using the product rule for exponents. 5 to the 3 a plus 3 equals 5 to the 3 a times 5 to the 3. Now, we know that 5 to the a equals 7, so we can write 5 to the 3 as open parenthesis 5 to the a close parenthesis cubed, which is 7 cubed. And 5 cubed is 125. Finally, let's calculate 7 cubed. Our problem is to compare the following numbers: 2 to the power of 11, 8 to the power of 4, and 16 squared. To compare these numbers, we need a strategy. The best approach is to convert all expressions to the same base. Since all of these numbers are powers of 2, let's convert everything to base 2. Let's start by converting 8 to the power of 4 to base 2. First, we need to recognize that 8 equals 2 cubed. So, 8 to the power of 4 equals 2 cubed, all to the power of 4. Using the power rule for exponents, when we have a power raised to another power, we multiply the exponents. So, 2 cubed to the power of 4 equals 2 to the power of 3 times 4, which is 2 to the power of 12. Now, let's convert 16 squared to base 2. First, we write 16 as 2 to the power of 4. So, 16 squared equals 2 to the power of 4, all squared. Using the same power rule as before, we get 2 to the power of 4 times 2, which equals 2 to the power of 8. Now that we've converted all the numbers to the same base, let's summarize what we have. We have 2 to the power of 11, 8 to the power of 4, which equals 2 to the power of 12, and 16 squared, which equals 2 to the power of 8. Since all numbers are now powers of the same base, we can compare them by comparing their exponents. The larger the exponent, the larger the number. So we can arrange these numbers from smallest to largest as follows: 16 squared, which is 2 to the power of 8, then 2 to the power of 11, and finally 8 to the power of 4, which is 2 to the power of 12. This is a challenging comparison problem that requires understanding exponent properties and building logical inequalities. To solve this problem, we need to find a clever strategy to compare these very large numbers. Let's start by comparing 13 cubed with 2 raised to the power of 11. we can calculate that 13 cubed equals 2,197, while 2 to the power of 11 equals 2,048. So we can state that 13 cubed is greater than 2 to the power of 11. Since we've established that 13 cubed is greater than 2 to the power of 11, we can raise both sides of this inequality to the power of 13. This preserves the inequality direction because we're raising both sides to the same positive power. Using the properties of exponents, we get 13 raised to the power of 3 times 13, which equals 13 to the power of 39, is greater than 2 to the power of 11 times 13, which equals 2 to the power of 143. Now, we need to connect this to the original problem involving 4 to the power of 71. Let's analyze 4 to the power of 71. We know that 4 equals 2 squared. So 4 to the power of 71 equals 2 squared raised to the power of 71. Using the power of a power rule, this equals 2 raised to the power of 2 times 71, which is 2 to the power of 142. Now we can see that 2 to the power of 143 is greater than 2 to the power of 142 because the exponent is larger. Now we can build a chain of inequalities. We know that 13 to the power of 40 is greater than 13 to the power of 39, which is greater than 2 to the power of 143, which is greater than 2 to the power of 142. Therefore, 13 to the power of 40 is greater than 2 to the power of 142. And since we already showed that 2 to the power of 142 equals 4 to the power of 71, we can conclude that 13 to the power of 40 is greater than 4 to the power of 71. In conclusion, we have proven that 13 to the power of 40 is greater than 4 to the power of 71. Let's review our approach. First, we found manageable numbers to compare, 13 cubed and 2 to the power of 11. Then we extended this comparison by raising both sides to appropriate powers. Finally, we connected back to our original problem by expressing 4 to the power of 71 as 2 to the power of 142. This problem demonstrates the power of strategic comparisons when dealing with very large numbers. Can you try a similar approach with other large exponential expressions? Pause the video and try comparing 2 to the power of 100 versus 10 to the power of 30. Today we'll learn how to compare large exponential expressions without calculating their actual values. Specifically, we're going to determine which is larger, 17 to the power of 13 or 7 to the power of 17. When comparing expressions with different bases and exponents, we need a clever approach since calculating the actual values would result in extremely large numbers. The key insight is to transform both expressions to have the same base, which will allow us to compare just the exponents. Let's begin our analysis with the first expression. We have 17 to the power of 13. First, we'll use the fact that 17 is greater than 16. This means that 17 to the power of 13 is greater than 16 to the power of 13. Now, we can rewrite 16 as 2 to the power of 4. So 16 to the power of 13 becomes the expression 2 to the power of 4, all to the power of 13. Using the power rule for exponents, when we have a power raised to another power, we multiply the exponents. So 2 to the power of 4, all raised to the power of 13, equals 2 to the power of 4 times 13, which is 2 to the power of 52. Now, let's analyze the second expression. We have 7 to the power of 17. We can observe that 7 is less than 8. This means that 7 to the power of 17 is less than 8 to the power of 17. Similar to our approach with the first expression, we can rewrite 8 as 2 to the power of 3. So 8 to the power of 17 becomes 2 to the power of 3, all raised to the power of 17. Using the power rule again, 2 to the power of 3, all raised to the power of 17, equals 2 to the power of 3 times 17, which is 2 to the power of 51. Now we can directly compare our expressions in terms of powers of 2. We have 17 to the 13th power is greater than 2 to the 52nd power, and 7 to the 17th power is less than 2 to the 51st power. Since 2 to the power of 52 is greater than 2 to the power of 51, and the first expression is even greater than 2 to the 52nd power, while the second expression is less than 2 to the 51st power, we can confidently conclude that 17 to the 13th power is greater than 7 to the 17th power. Therefore, our answer is that 17 to the power of 13 is the larger expression. To summarize our approach, we converted both expressions to powers of the same base, which allowed us to compare their exponents. This method is powerful for comparing expressions that would be too large to compute directly. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.